G'day guys, it's Mr. Bennett here. Today we're going to be going a little bit further in terms of looking at our ionisation energies. Alright, so we're going to see how this works and how this affects the spectrum. Alright, so I've just drawn a sample of like the shells for an electron shells for an atom. Okay, keeping in mind that we have down the bottom here is our nucleus. Okay, our nucleus is down the bottom here. Alright, closest to the ground state, and so obviously the electrons want to be as close as they can to the positive nucleus, alright, because obviously opposites attract. Now if we were looking at the particular energy transitions that can occur here, so when I excite this particular gas up, let's say I excite a electron up to here, alright, up to that shell there, because I'm only giving the energies for those. What would be possible is that electron could fall from there to there, could fall from there to there, it could fall from there to there. So that's one possibility. It could also fall via this position here down there, or it also could fall from this position straight down to there, from there, or it could fall from there to there. Alright, so I think I've covered all the possible transitions. So if I had enough energy to excite my electron up into this position, then that's what I do. So if I actually had 12.1 electron volts worth of energy, I could excite an electron up to there, couldn't I? Alright, so in this scenario, what's going to happen is we're going to have a whole range of different particular things that we might expect to see. So in this particular one, I would expect to see 6 lines in my spectrum. Okay, this would be a line emission spectrum. Sorry, I don't know what I've done there. So emission spectrum. So it's called a line emission spectrum. Right, so the energies that these things are going to have is the gaps between the two shells. So if it fell from the third excited state or to the second excited state, it's going to lose. Now every time it transitions there, what happens is a photon's given off. Okay, every time it falls down, conservation of energy means a photon's going to be given off with that amount of energy. Alright, so the energy between the shells is going to be how much energy these photons are going to have. So 12.1 take 11.4 is going to give me 0.7 electron volts, will be one. It could also fall from the third excited state to the first excited state, and that will give me 1.9 electron volts. If it went from the second excited state to the or third excited state to the ground state, that would give off 12.1 electron volts. If it went from the 11.4 down to 10.2, it's going to be 2.2 electron volts. And then it could fall from there, from the second excited state to the ground state, 11.4 electron volts. Or it could go straight from the first excited state to the ground state, which would be 10.2 electron volts. So I've actually found the energies of all these lines. Now what we do know is that energy is related to what? Well, energy is related to the frequency, which is related to the wavelength. So we know energy is equal to HF, which is also equal to HC all over the wavelength. So if I wanted to work my wavelength out, then what I need to do is simply have H times by C, divide that by my energy, and that would give me what my wavelength is. Now my wavelengths are here, my energy is actually in electron volts, I'd need to convert that to joules. So let's have a go at that calculation. Let's do the first one, 0.7, and we'll do the 10.2 one, just to show you the sort of energies that you're going to get here. Alright, so if I do that, it's going to be, the wavelength is going to be H, so 6.63 to the exponent minus 34, times that by the speed of light, which is 3 to the power of 8, and then I have to divide that by, now I've got to convert 0.7 electron volts into joules. timesing that by 1.6 to the exponent of minus 19, and close my bracket, and then go enter. So that's going to give me something like 1.77, alright, so 1.78 by 10 to the minus 6. So this one here gives me a wavelength of 1.78 by 10 to the minus 6 meters. Alright, let's do the other extreme. Let's do 10.2. So quick way on your calculator just to bring up the last thing you did, and just scroll back to where I put in my thing over here. And now what I want to do is I want to go 10. Now I have to insert 10.2. Okay, and then I should be ready to go, and that's going to give me 1.21 by 10 to the minus 7. Okay, so that's equal to, so this one here is equal to 1.21 by 10 to the minus 7. Alright, so this one here I could say is equal to 17.8 by 10 to the minus 7. So if I'm looking at that, I've got a value down here which is 1.21 or 121 nanometers by 10 to the minus 7, or I've got this one over here which is 17.8 nanometers. Now, considering our range of light that we see, is we're going to see light which is between where? Right, somewhere between 400 nanometers and 750 nanometers. So that's 17.8 times 10 to the minus 7, which is going to be 1,780 nanometers. Sorry. Right. So we're going to see light in that region there, but in fact these two things aren't going to actually appear in that region there. But what you'll see when you start looking at the visible light, there'll be some that actually fit in that region. Alright, so what you'll see here though, for each of these transitions from each of these energy levels, you'll see a particular line corresponding to that. These lines will have distinctive colours. So in the visible light, you're going to see different colours based on what their particular wavelengths are. Alright, and so we'll only particularly see this, but there'll be other lines in sort of the infrared and the ultraviolet spectrums that you won't actually see. Alright, so this tells you what actually happens when we start looking at the transitions between energy levels. Now, the true thing and the great thing about this is it provides evidence that electrons or atoms have electron shells of fixed states of energy. So therefore, what we're seeing here when we start looking at the line emission spectrum is we're seeing the particular energy gaps between these levels, right? And these things correspond to those. Now, the great thing about this is how it's actually used is certainly in astronomy, we look at the light by knowing what particular certain types of atoms or certain types of elements have their wavelengths will give us an idea about what sort of light we're looking at. So that will be a really useful thing to analyse when we actually start looking at for real. Anyway, we'll talk about this in our next video, so hopefully that sort of made sense what we went through here. Yeah, there's some questions for you to do in your workbook that relate to this, alright? So catch up with me if you need some help.